Okay, this is another exercise, the material related to the gas. Okay, so we know that the questions tell us the gas, the gas escapes through a small hole. So there is a small hole, and the whole area showing here. So we have the whole area is 10 minus 7 meters square, and the total volumes in the tank is the 10. So we know that the volumes is the 10 meter cubic. Okay, and the question tell you the gas escapes so slowly, and the temperature in the tank remains constant at the 32 degree. So we have the temperature, and this is a 33 degree, and we can minus, we can plus 273 to convert the temperature to absolute temperature. Is equal to 296 K. The mass flow rate of the gas through the hole is given by the mass rate equal to 0.666 pressure inside the tank, and multiply the areas divided the root of the R and T. R is the gas constant. So for these questions, we first define the control volumes as the dashed line showing here, and the inside is control volumes. The dashed line is control service. So the question is, please calculate the time required for the absolute pressure in the tank to decrease from 500 to 400 kilopar. So the P0, the initial pressures is 500 kPa, and P is the final pressure is 400 kPa. Okay, so there are the parameters we will use in later. So first, we follow the continuity equations. The total volume in the mass in the control volumes change with the time plus the outflow mass rate minus the inflow mass rate. For these problems, we don't have the inflow mass rate. We only have the outflow mass rate related to the small hole, the gas escape from the small hole. So we have the only have the one end rate. Outflow is equal to 0.66 pressure areas divided the root gas constant multiplied absolute temperatures. So this is our equation 1, and the mass in the control volumes is equal to the mass shell plus the mass of the tank. So we know that the tank volume is V, and we have the density of the volumes of the tank. So the density multiply the volume. Okay, and we can compute the differential dmCV dt is equal to dm shell dt plus d rho dt multiply the total volumes plus the rho multiply the dv dt. And then we check that the mass shells didn't change with the time, and the volume of the tank also didn't change with the time. So for these equations, we only have the d rho dt multiply the tank volumes. But why we have the densities can be changed with the time, because our material for these problems is gas. The density of the gas can be changed with the different times. Okay, so we reorganize the equations here. dmCV dt is equal to the d rho dt multiply the tank volumes. Okay, and here's our problems. We only know that the condition is the pressure changes. So for this equation, there is no pressure parameter. But based on the ideal gas law, we know the pressure is equal to the rho RT. So we know that the rho density is equal to the pressures divided RT. Okay, so we replace the density by the ratios between the pressure and the RT. So here we can rewrite keep the volumes and multiply the dp dt, and the RT is the gas constant, the absolute temperature are the constant values. So I just take outside. So here is the divided RT. Okay, this is our equation 2. So we have the equation 1 and the equation 2 put back to the continuity equation showing here. Okay, we have the 1 and we have the 2, and put to the continuity equations. So we know that the V divided RT and the dP dt plus the equation 1 and mass rate for alpha here. So this 0.66 pressure areas divided RT is equal to 0. Okay, and dp dt, and the v divided rt. Then we move a second item to the right hand side to become the minus 0.66 pressure areas divided RT. Okay, then we move to the constant parameter to also to the right hand side. So, and then we move the P parameter to the left hand side. So we have the dP P. And the right hand side we have the minus 0.66 pressure areas and divided the volumes and multiply the RT divided the root RT. So it's equal to root RT and dt. Okay, so right now, based on this formula, we can process the integrations from the pressure initials to the pressure finals, and the layer right hand side is for the time parameters. So we start from 0 to the time finals. Okay, so here we process the integrations. So this is equal to the rho p, and the interval of the pressure start from P0 to P final. The right hand side is the minus 0.66 pressure areas divided the total tank volumes. We have the root RT and multiply the TF. And the TF is the answers for our questions. It's time required. Okay, so and then here this is equal to ln PF minus the ln PN, but we have the minus in here, so we can move to the left. So the left item to become the ln PN minus ln PF, and this is equal to the P ln PN divided the PF. And then I move to the right hand side items to the left hand side, and so there is multiply the volumes and divided the areas. Okay, sorry, so there we don't have the pressure item in here. Okay, and divided the 0.66 over 1, and also divided the root RT over 1, and the right hand side we only have the TF. So we move to here, the TF is equal to ln pressure ratios. The P0 is 5, and the P final is 400 kPa. So there is the 500 kPa divided the 400 kPa. Okay, and divide, multiply the 10. The 10 is the tank volume meter cubic. Divided the 10, the area is 10 minus 7 meter square. And divided the 0.66 over 1 and divided the root. The gas constant showing here is 518, and the absolute temperature T is 296. Okay, so sorry. Okay, you can use your calculator to calculate the answers. So the first is 5 divided 4, and the pressure ratios. So this is long pressure ratios is 0.223, and this item is equal to the 10 8 powers, and divided the 0.66 over 1, and divided the root 518 multiply the 296 absolute temperatures. So this is equal to 391.6 over 1. Okay, so you can compute the TF. Sorry, there is the root over 1. Okay. Oh, I already take the root values. So this is again the root 518 multiply 296 is equal to the 391.6 over 1. Okay, so 0.223 divided the 0.66 and divided the 391.6, multiply the 10 8 powers is equal to 8 6 2 8 1.6 seconds. Okay, so you can calculate your answer. TF is around these numbers, and the number of the seconds showing here is quite close to 1 day. So that means the pressure change from the 500 kPa to 400 kPa. The time required is quite slowly, and the gas is escaped from the hole. It very slowly based on the mass flow rate showing here, and we know that the pressure is higher, the mass flow out is also large. Okay, so this is the exercise, but the material is not liquid. The material is the gas. Because the material is gas, so the density can be changed with the time. So this is very important. And the basic concept the idea is the outflow rate is not constant and will change when the pressure in the tank changes. Okay, so the next concept is continuity equation for flow conduit. So how different? Because this is a conduit, and we have the cross-section area along the one, and there is a cross-section along the two, and we depict the contour surface like the figure showing here. So the inside is our contour volumes, and this is the contour surface. So the idea for these questions in the conduit, the mass in the contour volumes didn't change with the time because the pipe is always filled with the flowing fluid. So the inside the contour volume of the mass didn't change with the time. So as we remember, based on the continuities, our formulas for the continuity is dmcv dt plus m out rate minus m in rate and equal to zeros. When we write down the formula showing here, it's based on we know that the flow is uniform flow and the fluid flow directions is always parallel to the normal factor of the cross-section area. Okay, so the general formula is the d dt, and then we need to process the integration problem is a rho dv and along the contour volumes and plus the integrations along the contour surface, and we have the rho is the fluid density multiplied the velocity field factors and dot product with the cross-section area factors. Okay, and equal to 0. And because right now we consider conditions conduit and also based on the continuity equations, and we know that we don't have the mass changes in the control volume with the time. So this item is equal to zeros. So we can rewrite the equation based on the continuity ideas. So we know that the m rate out is equal to the m rate in. And we know that the integration problem along the control surface rho v factor dot product to the dA cross-section area factors is equal to 0 also. Okay, so this is very important applications for the continuity equation under the conduit conditions. So this slide just summarize what I said in the previous slide. Section 1 is outflow, and this is a section 2 is outflow, and the section 1 is inflow, and the minus each others is equal to zeros. And I have said that the m rate out will equal to the m rate in. So we know the mass flow rate can be defined by the rho and the Q discharge. And we can rewrite the discharge by if we know that the velocity and the cross-section area. Okay, so you can write the continuity equation for the conduit problems. It's rho 1 A1 V1 is equal to rho 2 A2 V2. This is very important under the pipe flow. But if our flow condition is unsteady flow, so the dmcv dt not always equal to zeros for the unsteady flow problems. So please notice that. But if you assumptions of the ideal flow, so this is the formula always satisfied for the ideal flow. Okay, so we can do very quickly for this exercise. This is what we know that is a conduit, and it's based on the pipe flow conditions. Okay, and we have the cross section 1 and the cross section 2, and we depict the control surface as the dashed line showing here. So inside is the control volumes. Okay, and because this is the pipe flow, so we know that the MCV didn't change with the time. So we have only the M rate in is equal to the M rate out. And then in here, the cross section 1 is related to the inflow, and the cross section 2 related to the outflow. So the M1 rate is equal to the M rate 2. Okay, so we know that the rho 1 A1 multiplied V1 is equal to rho 2 A2 V2. And we assume this is ideal flow, so the flow condition is incompressible. So the rho 1 is equal to the rho 2. And for the questions, we already know the speed of the water in cross section 1 is 2 meters. So the V1 is 2 meters per second. Okay, and we have the velocity. So the question is, what is the water speed in the cross section 2? So we don't know the V2. So we can rewrite the formula showing here the V2 is equal to the V1 multiplied the A1 divided the A2. And we know this is the pipe. So the areas is equal to the 4 over pi diameter square. So for here, we know the A1, A2 ratio can be rewritten by the D1 divided the D2 square. And we just put the number inside the equations. So the V1 is 2 meters per second, and multiply the D1. The D1 is 1.2 meters. The D2 is 0.6, and we have the square. So the ratio value showing here is 2, and the 2 square is 4. 4 multiplied the 2 finally is equal to the 8 meter per second. Okay, so the idea is quite simple. we simply check the condition is the conduit problems. And the second, we know that the flow is ideal flow, so satisfy the incompressible conditions. So we know the V1A1 is equal to the V2A2. And try to process based on the continuity equation to answer. The question is what is the water speed cross section 2? Okay, so this is our today's class. So right now I move to the exercise, the pipe quiz. Okay, so I open the pipe quiz. So before the pipe quiz, I will explain the pipe quiz. 好，那我稍微说明一下今天的这个考试的这个题目。那题目一，大家注意一下，这个配分的比重是30%。那我们可以看到，他说的是有一个 pipe， 它的直径 diameter 是10公分，那里面是介质是这个我们的空气，那它的在20度 C 下的温度跟110 kPa 这个绝对压力的条件下，它的流动速度是34 meter per second， 请你决定它的 mass flow rate 是多少。那我这边有提供这个气体常数是287 for 这个 air。OK， 是求这个质量流率有多大，那这个配分是30分。那第二小题，第二题其实是需要你去了解一下怎么去运用这个连续方程。我们前面一直上到的这个 continuity 的这个 equation， 那他跟你讲说，在这个系统里面，我液体的表面积是0.1平方公尺。那我有一个 inflow， 有一个 outflow。那 outflow 这个位置会因为水深的不同，这个 h 的水深的不同，会有不一样的这个速度的outflow 的速度变化。那在这个 outflow 的位置的截面积是 0.003 meter square。那在这个 inflow 的截面积是 0.002 meter square。OK， 那题目这里面都有详细的说明，我只是用图来解释。那题目想问什么？他想问你说，在一个确定的时间的时候，我们知道这个水深是 0.9 米，那在这个时刻的抬升速率是每秒4公分。而且我告诉你，这个 liquid 是不可以压缩流。那请你计算此刻这个 inflow 的速度场大小是多大。那我们知道你可以先列出连续方程式。那我希望同学在计算这一题的时候，可以把你心目中认为处理这个问题的 control service 定义出来。那因为我们通常在处理连续方程的时候，都会将 control service 先画出来，我们才知道在 control service 上的交换边界有谁。那在 control service 的范围之内，我们叫做控制容积 control volume。那我们才知道这个问题要怎么用连续方程来处理。那希望各位同学可以把这个我刚刚讲的 control surface 跟 control volume 在这个题型里面定义清楚。好，那下一个我们这个 slide 我们会就停留在这里。停留在这里。那这是第一题跟第二题，那配分是30跟70分。如果同学没有问题的话，就可以现在开始作答。那作答方式，你只要最后上传 你的图档上传你的解答的详解的图档至助教在这个E3平台所开放的作业缴交区。那提醒各位，在缴交作业是有期限限制的。那在期限以后，同学就没有办法再上传这个你作答这过程的图档。那我们建议图档尽量以 JPEG 为主，那助教才不会有开启图档的这个问题。好，那我们就开始作答。 然后还有最后的2分钟，请同学在作答的时候，开始准备要做个收尾。那记得在最后必须把作业这个作答这个过程的影像档上传至E3的这个平台。好，我们时间到，请各位同学务必记得要去上传啊这个作答的这个过程。